Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my great pleasure to welcome Craig Nobrock to come here to give us a talk. And Craig is a senior project leader at ISI, and he's also a research professor at USC, and he's also a chief scientist from Fetch Technology and GeoAssembly Technology. Both of them are spin-offs from USC, and he's my fellow Caligmano alumni, and he has published many books, articles, and served in senior program committee for many AI conferences. And he's a co-chair of the 2008 Triple AI track of AI and the Web, and he's a conference chair of 2011 Ichikai. And he's currently president of the International Conference on Automated Planning and Scheduling, a trustee of International Joint Conference on AI, and a fellow of Triple AI. Okay, without further ado, let's welcome Craig.
Great. Thank you very much. Okay, so today I'm going to be talking about work we've been doing at USC on building mashups by example. And I want to acknowledge my collaborators, since Rattapoom Tuchinda, who's a PhD student who's working on his PhD, has really been the driving force behind a lot of this work, and I have to certainly give him credit. And then Pedro Szekely, who's also at the University of Southern California. We've been jointly advising Rattapoom on this work. So I'm going to delve down and talk more about the work we've been doing on this topic. So I'm sure most of you are familiar with mashups, and you've seen all kinds of sort of interesting mashups that are out there these days. But just for review, a mashup is basically, some kind of application that combines the content from one or more source to provide some kind of unified or integrated experience. And there's lots and lots of examples of mashups out there. Some notable ones are, things like, taking crime data and putting on a map. Those are the simplest kind of mashups, where you're simply taking some set of data that's been published in one place and sort of say, okay, I'm going to combine it with this other application. The Google Maps thing seemed to be launched the mashup craze, where everyone was just taking things and sticking on top of Google Maps. But there's lots of other examples of these now. Zillow is another example, and it's not, strictly speaking, a mashup, but it has the same flavor, where they're essentially taking all of this very interesting information about property from a whole variety of sources, putting it together, sticking it on top of a map, and then providing sort of a unified experience there. One of my favorite ones, the one on the right here, Skibonk, is one where they've basically taken all the information about locations of ski resorts, combined it with weather data, and then stuck it on a map, so that in a glance you can decide whether or not and where you want to go skiing that day. And no one of those websites by themselves actually provides all the information in one place. There'll be one website that has the listing of all the ski resorts, another one that's got the recent weather conditions, and so to put it all together in one place often provides something that an end user might want. And this is sort of the point, which is that what an end user wants depends on the user, right? Every user is sort of looking for something different. And for whatever mashups that are out there, there's always some new mashup that someone wants, right? There's some new user that says, hey, if I could take the data from here and put it over here, that would be really great. Then I could do this. And today you largely have to wait for someone to build you that mashup. And typically, the combined data gives you some new insight or provides some new data or service that's not there in any existing web source. Now, if you look at sort of the trends for mashups, this is just a screenshot from the programmable web, and it shows you, the new mashups that were constructed in the last 6 months. And you can see that people are building these all the time, but these are largely programmers, right? They're people that are using either programming them from scratch or using some kind of programmatic tool to actually create these things. But you can see that the interest in these things in general is quite large, right? This is the total number that have just been posted on the programmable web, which is up to, almost 3,200. And at the bottom, they're divided into different categories here. So these are just to give you a sense for the different kinds of things. Mapping tends to be the biggest one, right? That's the largest part of the pie here. But there's all photo, shopping, search, video, travel, and so on are all different kinds of mashups that people are creating. So the focus on this particular work is really on things related to the first 4 categories that we often see: mapping, photoshopping, and search. And those accounted for roughly 47% of the most popular ones that are out there. There's no reason it couldn't be expanded to the other ones, but different types of mashups have sort of different properties and different kind of user interface requirements. Okay, so let me talk now about sort of the different mashup building issues. Okay, and there's sort of a set of general problems that have to be solved in order to create mashups. The first one is, of course, the data retrieval problem, right? And we've been working on sort of web-based extraction for many years now, and there's been lots and lots of work. But the point is that somehow you have to get the data to build the mashup, right? And maybe it comes from some nice API where you can just query the information, but more often than not, it's stuck on some HTML page that you've got to navigate to and pull the information out. So that's the first problem. And the typical approach today is to have some kind of wrapper technology, which basically goes from a site that looks like this to something that's in a more structured form that you can actually get the data. The second issue is sort of the calibration, and this consists of 2 pieces. One is what we call source modeling. So you pull the information off. You typically need to know something about what this information is actually providing. Is it a date? Right? Is it the name of a restaurant? I mean, so there's a whole variety of things that you might actually be pulling off of that web page, and you want to understand what this source is actually providing. And that becomes very important when you want to do some kind of integration with other sources and so on. The second one is data cleaning, because what you typically find when you integrate data across sources is that there's all kinds of minor variations that sort of get in the way of actually presenting the information in the form you want or combining it with another source. And I'll describe some examples of these, but these might be simple things where in one case the name is abbreviated, in another case it's not, or it's been rearranged in some way, or if it's a date format, what are the huge number of variations on date formats do they use, and if it's different than another format or the one that you want, then those kinds of issues can be a problem. The next issue is the integration. So what happens in a mashup typically is that you want to actually combine the data in some way, right? The whole idea of the mashup is to put more, 2 or more applications together. Maybe you're just going to one source and you're just restructuring it in some way, but typically you're really trying to combine the information in some way. And the challenging part here is to actually specify in what way you want to actually combine the information. And then finally, there's the display issue. How do you actually want to, once you've decided what sources I'm going to get the data from, and you've cleaned up the sources, and you've modeled them, and you've integrated them, well, then there's still the presentation issue. And, for the most part, in this talk, I'm not really going to talk about the display issue. That's a whole thesis project in itself, which we haven't done yet. So we're going to focus on the other issues here. And I should mention more generally that, these type of mashup building issues, these are the general information integration issues that people have been working on in general for the last 20 years, 30 years. But what's different here is, the real focus of our project is enabling the users to actually do these things, right? That we're not trying to just automate these different tasks and put them together and magically create the mashups for the users, but really to come up with a framework in which we can actually support the user that wants to create the mashup to actually solve these problems. Okay, so now I'm going to go through just a few different types of mashups, and you'll see in our experiments that we actually use these particular types to do experiments and so on. So, a very simple type of mashup might be one where we simply do the retrieval, do some modeling and cleaning of the data, and then just display the information on a map, for example. Right? That's sort of the simplest kind of mashup you want to build. And that would correspond really to the Google Maps type mashup that are really popular. The second type is some kind of a union. And these are quite common too. So maybe I have 2 different restaurant review sites that I go to, and I say, well, wouldn't it be great if I had all that information in one place and it was put on top of a map so I could sort of see the information. So now you get into a little bit more challenging kinds of issues, because now we need to solve the problem of extracting the information from the sources, and then deal with the sort of the calibration issues here, and then specifying how you're going to combine it. Unions are usually pretty straightforward, right? You're just combining the sources, the data, and just appending all the data together so you have the combined set of information. Although this can potentially get into more complicated problems if you want to deal with things like deduplication, right? If you had overlap between the sources and stuff. But you'll see that in many mashups they don't deal with that at all. They just do a very simple kind of pull the information together and display it. And then finally, you want to create some kind of integrated interface or something like this is just showing a map kind of interface. We've taken the data and just displayed the points on the map. The third type is very close to the first one, except that now instead of just doing straightforward extraction from the web page, now you're doing some kind of interaction with a web form, right? There's a whole lot of data that you can get that's sort of behind a web form where you go and you enter some information and then it then provides some data. And then you go through the same kinds of things where then you're going to do the cleaning and display. And then the last type here is really some kind of join where, before we had a union, which is where you're just taking the data and combining it into one large table. Now we want to take the data and actually combine it, where you're essentially saying, well, I might have a set of information about restaurants, and I want to put all that information together. I want to relate the information across the different restaurants. And this typically is harder to specify because usually what you're doing is you have to specify, well, which restaurant in one source corresponds to which restaurant in another source, for example, doing those combinations. And so somehow you have to be able to show to the system how you're going to combine the information. All right. And then, the last type that we're not really going to talk about is sort of this customized display. How do you actually deal with that? And that really sort of spans all of these, right? Because almost every mashup has some kind of display because usually the user wants to present it in some way. But I'm not going to spend time talking about how to solve that problem today. Okay. So existing approaches, basically the goal of this work is to create mashups without programming. And the problem today is with the existing approaches, it doesn't turn out, you have to have some basic knowledge about programming, it turns out, in terms of the way the existing systems actually work. So here's a screenshot from Yahoo Pipes. For those of you who haven't seen it, it's basically a tool. Yahoo Pipes is actually a tool for creating mashups across web services, right? So you have these service-based interfaces, and you're really describing how it is you're going to integrate the data across these different services. And what you see is it's based on this widget paradigm, where you have these different widgets that you place on your desk on the screen that where you're building the mashup, and they perform operations on the data, and they can specify ways of extracting information from different kinds of feeds. They can specify different ways of putting the information together and stuff. It's not, you don't have to write Java code, but at some level, you're still in this sort of paradigm where I have these operations on the data, and I'm going to put the operations down, and I'm going to specify how I'm going to connect the operations up. This type of approach is also used in Microsoft has a system called Microsoft Popfly. Similar kind of thing, except they have even more widgets. But typically what happens for the users, they have to spend a lot of time essentially locating and learning how to basically customize these widgets. They're typically quite powerful. You can write regular expressions. You can do all kinds of interesting things with them. And they're really great for programmers because we're used to that kind of paradigm. And they focus, typically the existing systems focus on some of the issues that I just went through, and they ignore other ones depending on what the focus of the project is. So one of our goals then is to come up with a framework that addresses all of these issues while still making the mashup building process easy, right, for the end users. And our target here was not programmers, but people that maybe haven't had a lot of experience programming, but want to create their own mashups. Okay, so here are sort of the key contributions in terms of what we've done. We've developed this programming by demonstration approach that uses a single table for basically building the mashup. The table, in some sense, is the unifying framework for the user to interact with. It then provides this, an integrated approach that actually combines these different pieces. So in a lot of systems today, the different components that I described, the data extraction, the modeling, cleaning, and the integration, are each sort of their own piece in the system, right? You go and you solve this problem, and then once that's solved, you go to the next problem. And we really try to treat this more uniformly in the sense that it's all embedded in the same paradigm. You're using the same user interface, so it's a little more natural for the user. And we allow the system to actually build fairly sophisticated kinds of queries, but do it using the same paradigm. So using the programming demonstration idea, you can actually write what under the hood are fairly complicated queries, but the user doesn't see them as necessarily complicated queries because they never write a query. So some of the key ideas here then are we focus on the data and not on the operations, right? The users are most familiar with the data. In some sense, they know what the data is that they want to extract, and they know in some sense how they want to put it together. And the idea is that the user then manipulates the data instead of manipulating the operations. Another key idea here is to basically leverage the existing data. And the idea here is that, over time, if I'm interested in a particular topic and I'm building mashups on that topic, then I'm going to build up a repository of sort of previous data sources and things that I've created in the past. And this can help you a lot in terms of doing the modeling, where I'm describing what this source is actually providing, cleaning the data, so the same type of operations that I need to perform, I may have performed in the past, and then doing the integration piece. And so, and the other thing here is that, as opposed to most problems in computer science where you usually want to do some kind of divide and conquer, we really took the approach that, that by pulling these pieces together and solving them as sort of one integrated piece, it's more natural to the user, and solving one issue can also help solving the other issues. Since the different components here that we're talking about are often very closely interconnected, so often it's very hard to actually completely separate them. And we do this by interacting with this sort of single table or spreadsheet kind of platform. Okay, so we've developed this system called Karma, and let's see, this is just a screenshot from the system. And so what you see here is on the left you have essentially an embedded browser, which is the focus has largely been on extracting from web pages. And so we've got a browser built right into the interface here. And then the idea is that you can then do sort of simple kinds of cutting and pasting into the table. So on the right here we have the table, and so this is the actual table that the user is really interacting with, and it's very close to the sort of the spreadsheet model that a lot of users are familiar with. I mean, even non-programmers often have worked with spreadsheets and stuff where you just have this sort of table of data that you're manipulating. And then here on the bottom are sort of the interaction modes, and this is the way for the user to sort of specify, what mode in the system that they want to be in. You may not be able to see it very well, but it has the different tabs here to sort of specify what step in the process that they're currently working on. Okay, and so now let me just go through sort of a motivating example. So let's say that you have a source of data on restaurants, and so you want to pull in, the restaurant name, address, phone number, review from, some restaurant review site, which is shown on the left here. This is the starting place. And then on the right, what we have is the LA County Department of Public Health, where every restaurant in LA County actually gets rated on a regular basis by this department. And you'd like to know, okay, I want to know when this restaurant was last inspected and what the score was, because I don't want to eat on sort of any substandard restaurants. And I want to basically do something very simple, which is pull these two sources together, clean up the data, and then display it on a map. Right? And so what you see here is sort of there's the extraction step here where I'm going to pull off the basic set of information, name, address, phone, and review. Over here I'm going to pull off again the name, address, but here I have the date of inspection and the score. And I want to clean up the data and then combine it, do some kind of integration here across the two sources, and then stick it on a map. Okay, now for the example that I'm going to use in the rest of the talk, I'm going to assume, just to simplify the talk, that essentially I've already done the shaded part here, and I've stuck it into a database. So I've got a database with the same set of information, right? So it's basically the same task, but I won't have to go through both parts of it. Okay, and in this database, this is sort of just the general database that you have as part of the system, which contains all the past sort of mashups that you built, which as we go along, we'll see this can be useful in actually creating new examples. All right, so let's start with the data retrieval task. There's been a lot of work on extraction. There's a variety of tools and stuff. And we took a relatively simple but sort of very easy to use type of approach, where you're essentially you're looking at a web page. So we've got the web page here on the left side. And what we're doing is basically copying the information into the table to essentially show the user what information we want to extract. And what's happening under the hood is that we're using this very common sort of approach, which is to exploit the document object model underlying the page. And by doing that, you can very quickly sort of generalize on the page to figure out what the information is, right? And so what happens then is the system basically builds the XPath expression that describes the information that you're extracting, and then does some generalization over that. So you can see, well, he only pulled in Japan Bistro, but really his intention is to say, well, what I want are all of the things essentially at that level in the document object model. So the model is shown, the document object model here is shown on the left, right? And so the user originally pulled in this, but this system can fairly easily generalize over this type of model and say, okay, it looks like, it corresponds to some path that essentially corresponds to this XPath expression here. And then, with one example, which is very nice here, you can get the complete list of all the restaurants on the page. Yes?
Did the user drag that? Or?
Yes. Yeah. So it's a little hard to show that on the slide, but the idea is that the user basically copied and pasted or dragged that over from the actual web page. Okay. So we've got this first level that we can get from this, and there's a number of tools out there that are using this kind of model. I will mention that, since some people have asked about this, that one of the issues with exploiting the document object model is that it works where it works, and then where it doesn't work, then you're kind of stuck. But for quite a few web pages, it works quite nicely. But one of the things that happens is that lots of times it's not enough just to get the information that you want from a single page. So typically you have to do some kind of navigation, right? So on this particular page, when I click on Japan Bistro, then what happens is it brings up this whole other page here, which is shown here, which now contains maybe the address and phone number for the restaurant and a little picture. I think in this case it even has a little movie you can watch. But it also has, the reviews, or at least the number of reviews on this page. And so you may actually want to extract some additional information here, right? So instead of just the name, I may want to get out the address, maybe some kind of description that's there, the number of reviews, and so on. So let's take the case where here I want to extract the reviews. Now I have a problem that, well, the reviews weren't shown on the original page, right? So the original top-level page didn't show the reviews. So somehow I have to connect up this detail page with the page that's above it. And so what's really going on here is that, in the original document object model, I had the name, the address, and then some brief description about the restaurant. And what I'm going to do then is use that information. Well, use the name, which is on this page, to then, and the URL, there's the underlying URL that's linked to each one of these names, to then link to the detail pages so that I can get all of these additional, the reviews, or at least the number of reviews off the next page. So what's really happening there is that we're basically building this XPath expression that's basically going to traverse these simple kinds of URL links, so that when you have a page and then it links to some sort of kind of detail page, which is very common, then it really is just going to connect up the pages across these things using those kind of URL links. So then we can basically fill out the table. And so what all the user's doing is essentially navigating to this next page, saying, I want the number of reviews here, copies this in, and then the system just figures out what the navigation path was through there. Yes?
The ranking on top of the page, is it mandatory for users to register in the system to participate in the ranking of the page?
You mean for the underlying website? So the question is does the user have to register to actually use these pages? I mean, typically, depends. What's that?
To rank the pages.
Oh, to rank the pages.
Yeah,
no. So in our system, all the user's doing here is going to the pages and pulling out the information they want. So there wasn't necessarily any kind of registration process. They're simply going through and saying that what the task the user's trying to do is to just aggregate the data about what are the restaurants that are listed here, and then how many reviews were actually available for each of the restaurants.
That means that you cannot track this with the users. For example, they can come to the system and rank a page, and we only have the IP address of the user. My question is that can you trust the ranking of the page in this way? Because the user can create a page, and he himself will for the page.
Well, the task we're trying to solve is that there's a set of websites that are available out there, and it's up to the user to decide what it is they want to do. I mean, what sources they want to combine, which sources they actually trust, and how they want to use the data. So we're not really taking a position on that. It's usually that people decide for themselves which things they want to trust. And what we're really trying to do is provide the tools that allow the end users to basically say, hey, I want to take this information over here and combine it with this other source over here and put them together.
And the other users extract information from the databases that organization link to your mashup system, or just from web pages?
Well, there's no way to link to our mashup system, so we're
Problem from Orange County. So how do they store the information about restaurants in their databases or in some web pages?
Yeah, we don't know, and it doesn't matter to us, right? It's on the web. It's all the data. I mean, we're basically assuming here that all the data is on the web and is distributed around. We're not taking a position on how they store it or how they access. Our assumption is that we have access to it, through a set of web pages that we can extract.
The web page is not important to the system.
Oh, it's very important. But the key here is that we're trying to support the user, right? A lot of people in the past have looked at information integration, myself included, as a process where, I specify a query and the system goes out and, magically pulls some information together, integrates it and presents it to the user, and the user is not involved in the process. The goal with this project is very much the user is deeply involved in the process, right? What we're trying to do is allow the user to build their mashup, right? So you say, I want to actually build this mashup where I combine the restaurant data with the health rating data and stick it on a map. I've decided, I've already spent the time to evaluate what the sources are that are available, how I want to combine the information, which information I want to use, and which information I want to use. And I'm basically creating, the tool that I want. Yes?
How do you deal with the fact that a lot of sites really customize their pages to the user? So, for example, they would use, browser cookies to, if you go to Amazon, I would get a very different page from you, right? So how would you account for that?
Now, that's a really good question. We don't account for that today. And one of the things I should emphasize here is that we've taken sort of an initial approach at the different subproblems, and our contribution is not necessarily specific on the extraction or the extraction piece or the source modeling piece or the integration piece. It's really the unification across those different sources. And so for any one of those issues, and I have a related work slide at the end, I'll talk about what people have done. But for any one of these issues, we could spend a lot of time delving into all kinds of issues like that. And my position on that is, well, they're all sort of problems that are solvable in some way. But really what I'm trying to do is look at the big picture here, how you put these different components together, and then you could delve in more specifically. There's lots of tricks you can play with those kinds of things. You can either model what the cookies are actually representing, or you can actually, clear the cookies every time so that they're not there. I mean, there's a bunch of ways to deal with that. But in the system I'm talking about today, we ignore the problem. Any other questions? Okay. All right. So basically, we finished the extraction piece. We've basically exploited the document object model here. We can navigate through the page, pull out the information, and build the initial set of data that the user wants to work with. So the next step is for the system to build some kind of model of what this information contains. And this is useful for naming, for one thing, just so that you have reasonable sort of names about what the kind of information is you're displaying. But it'll also come up it turns out it's very useful with respect to the actual integration step. So we pulled out some initial data. Let's say here we have a list of some set of names. And we may already have some data in the system. So we may already have extracted the LA health rating. If you remember, I assumed that that information had already been extracted and placed into the database. You might also have some other sources of data. Maybe I've got a list, some information about artists, and maybe another source such as the Szekely site, which also has restaurants. And the idea is that you can use sort of previous information that you've previously modeled. So in some sense, these have sort of tags associated with it. These are restaurant names and Szekely ratings, and here's restaurant names, and here we have artist names. And so what happens in this step is the system uses essentially previous extracted information to try to identify things that it's going to recognize from having extracted them previously. And so here we find that, maybe we discover that, okay, of the set we've extracted here, we find that 3 of those occur under restaurant name in previous sources. 1 of them occurs under artist name. And so we're going to say, well, we're going to take the maximum one, or propose that. In fact, I actually think we, in the current version of the system, we actually propose all the possible ones that we've seen in the past, and the user can select one or say, no, this is a new one, I'm going to enter it. The next step here is the actual cleaning process. So the problem here is that I've got my extracted information, And here I've decided these are restaurant names. And I have all the other information, previously that I've extracted from other sources. So maybe I want to look at the restaurant names. And one issue that frequently comes up is that you get minor differences across sources, right? So you get problems with maybe there's a restaurant that's misspelled, or maybe there's some systematic way in which these have been changed. Probably not with restaurant names, but with restaurant names, you may just want to be able to identify that, okay, potentially there's some problems here. So here you see that Sushi Roka here is Sushi Roku there. And those kind of things are a real problem, right? Especially if what I'm trying to do is to actually combine the information from this new source with the existing source there, because then it's not going to realize that they're actually the same. And so, the way to do this, the way we deal with this is we really allow the user. There's really two kinds of capabilities in the data cleaning part. The first one is we allow the user to basically manually clean the data if they want, because sometimes that's what it takes, right? I want to build this, I want to combine the data, and there's places I'm just going to have to fix things. And so this is a simple sort of table interface where I've got the set of data here, and then it opens up three new tabs. One is sort of a suggestion of what it thinks this is supposed to be. The next one is what the user sort of provides as an example of what they wanted from this. And then the final thing here, which is this allows the user to sort of say, well, in some cases the suggestions may be right, but maybe I want to override it. So in this case, the user might open this tab and say, well, what I want to do is take this sort of number of reviews, and I want to enter, what I really want to do is get rid of the reviews, right? I'm interested, because later maybe I want to do some comparison and find the ones that have the most reviews, or have ones that have at least 10 reviews or something like that. And so the user enters 31 here. What happens under the hood then is the system goes through and basically tries to find the transformation that would get the system from this to this, okay? And we have a set of predefined sort of rule classes in the system, such as substring or take the first token or take the last token, those kinds of things. So you have a set of predefined tokens, and the system then computes, based on the examples. It says, well, can any of the rules actually compute that? If not, it won't suggest anything. But if it can, then it'll actually generate the suggestion. Unfortunately, this table doesn't fill this out, but it would generate all the suggested ones based on this rule. And then the user can essentially confirm this and say, okay, yeah, this is the transformation that I want to apply here. So there's really two types of cleaning that go on. One is that the user essentially tries to specialize a set of sort of generic rules to the particular case here so they can apply them to the cleaning. And the second one is to essentially allow the user to then override anything so that if there's noise in the data, they can clean it up. And that's a big problem on the web.
Important stuff. Successively refine the rules, so that first rule might work for 5, and you get to number 6, you go, well, this is kind of an exception, and so can you then apply something that then applies to everything?
That would be a great thing to have. Right now, basically, the system tries to come up with one rule that will apply across all of the data, but then allow the user to then do some final edits on it.
So it's like a two-stage.
Yeah. So you could then go back and maybe it missed one or two, and then you can clean those up manually. Yeah.
Right, do you see anything in that case where a user would want to drop in a regex or actually a piece of code in there?
We don't support that because it doesn't really fit in our model. I mean, you could argue that maybe you should allow them to do whatever, and you should probably have sophisticated kind of tools. But we really tried to keep with the original goal here of sort of trying to imagine that, okay, what's an end user really going to be expected to do? We know how to write regular expressions, but right, coding's not allowed exactly. Yeah.
Imagine the user would want something even simpler where they initially just selected the number 31 and copied that into the table rather than 31 reviews and then figure out how to further.
Oh, well, they could have done that. No, they could have done that in the original extraction. But in fact, that's one issue with the using the document object model approach, which is the easy thing to extract from the document object model is going to be those things that are at the level of the document object model, right? And so then all of a sudden, once you're down within it, now all of a sudden it becomes harder to pull out exactly that piece of information.
As well as the rule at the same time.
Yeah. Well, one of the things we're doing now, I actually think the document object model approach is somewhat limited. One of the things we're doing now is actually integrating in a more sophisticated learning approach, which then they could do exactly that. They could have gone to 31 to begin with. And so you could have other kind of examples, though, that aren't just extracting a subset. For example, let's say I have last name, comma, first name, and now I want to switch them around. that's a very simple kind of transformation to kind of show the system. The system could easily have seen that type of transformation before. So it could say, oh, okay, I see what the user's trying to do there. But it wouldn't be easy to extract it in the original page. Unless you'd extract it. I guess you could have extracted the last name and first name separately, but maybe then you'd put them together. Questions? Okay. Now we're to the data integration piece. And what happens here is, okay, I'm looking at a table of information that I have. And the integration is, well, I want to integrate some data with the table of data that I'm currently looking at. And what happens down here is I'm in the integration tab, and what's available to the user at this point is to essentially put data in any of these positions. So I can actually basically, if I add information here, then really I'm trying to specify some kind of union of the existing table with some other information. If I want to specify information over here, then I'm really trying to do some kind of join where I'm extending out the set of information that I want to combine with the data that I'm already looking at. And up here, the way it works is the system may provide a set of options, which are things that it can sort of see how it could join with the existing data set to say, okay, these are additional attributes that maybe you want to add to the system. So what happens is that the user goes into this integration phase and essentially hits the fill button. And what gets generated then, if this is the original table and then these are sort of sources in my repository, then what the system does is it looks for ways that it could actually add additional information. So you can see here that the LA health rating, there's the actual health ratings for the restaurants, right? And for Zagat, here's the Zagat rating, which is maybe the food rating from Zagat's. And again, it can basically compute the possible potential joins across these different sources to sort of say, okay, this particular box, well, this data here could potentially be joined with this information over here because there's overlap in the restaurant and address. Likewise, this information here could be joined across just the restaurant name. There's no address information. And what happens then is we essentially compute these sets. Okay, so what happens in the user interface is that we have this set of information up here, which is these are the possible attributes that the user could actually select from some drop-down list. And then down here we have the actual values. And so the system actually computes potential values based on the database. So the user may know what the data looks like that they want to actually add here, and they can just select that to this. And so all of that gets computed based on the underlying databases that are available. And then the user essentially then, so the system then just expands out the information. So if I were to select, health rating at the top column, then it's just going to basically combine the information across these sources and propagate the health rating there. So it's easy for the user to do that. So let me go through an example, though, in terms of the more general example in terms of the types of queries that the user can actually specify. Right? So here's just a single column of information. And so what's really happening here is that we can compute at the top level in this is essentially going to be this is the top of the table, so this is going to be the attribute level. So we can compute all of the attributes that basically could fit into a particular column. And then here you have the cell level, which is these are the possible values that you could basically compute. And these are essentially going to be the attribute level is going to be this sort of set intersection across all these different values of all the different rows. And the values are going to be the place, essentially the values that are essentially consistent with that particular attribute, right, that you pick. So let's say here I stick in Los Angeles into this table. And I've got a source here that has information. There's a source, the attribute city, and it's got a set of information about tax property cities. I may also have a song name that matches Los Angeles, and it's essentially got information about pop music. And so what's going to happen in the other cells is I can actually put in values here that correspond to the other possible values that might correspond to both of those things, both a city and a song name. And then if I type in Honolulu, then it may find that, okay, this corresponds to city and same source that I had here. It may also correspond to some other source here, right? Favorite vacation spots. So then the question is, can you use this to help you determine sort of the plausible attributes for the table? And the idea is that, yes, you basically are narrowing it down essentially based on the information that you've seen there. And so you see once you have a few examples, you say, okay, that's likely to be city. We actually keep a drop-down list here so that it turns out that the system sort of conjectures wrong, then you can change it. The final step is the actual map generation. So the idea here is that we essentially apply sort of a general set of heuristics today to essentially look at the data that's in any of the columns and say, well, do I actually know how to place any of these kinds of things on a map? Right. So, is it a street address, in which case I can, run a geocoder on it, or is it, correspond to some, other type of, maybe a city name, right? In which case I could also place it on a map. Or is it a state name, for example? So there's just a general set of rules that allow it to take the data and stick it on a map. And if it's amenable to sticking on a map, then you just click a button and you say, okay, show me the data on the map. Otherwise, today we haven't really spent time on the user interface part of it. The display part of it. So otherwise today you're just stuck with either looking at the data as a table or sticking on the map. Okay, so let me spend a few minutes now and talk about sort of the evaluation of this. We used as a baseline a combination of a system called Dapper, which is a mashup tool that really focuses primarily on the extraction piece. It works quite nicely. It's very easy. There's a web-based interface you can go to and you can build these extraction things in Dapper. And we looked at that combined with the system called Yahoo Pipes, which I mentioned earlier is sort of more of a widget-based paradigm where you're basically using these widgets to connect the information up. And in the mashup community, it's actually quite common for people to actually combine different mashup tools. So people, in fact, oftentimes combine Dapper and Pipes. So it seemed like a natural way to do this. And these are popular and widely used tools. So we thought, okay, this is a reasonable combination of the tools to look at how it compares to our approach here. And what we wanted to do is look at a couple of different issues. One was, could we actually show that users with no programming experience could actually build the different mashup types that we have here? And then the second one is, could we show that Karma actually takes less time to complete each of the subtasks and scales better as the tasks get harder? And finally, overall, does the user take less time to build the same mashups in Karma as compared to something like Dapper and Pipes? And for users in this experiment, we had 20 programmers. These were essentially students in the course that I teach. That we gave them extra credit if they would run the experiment for us. And so we got a whole bunch of students that these are basically master students in computer science that have had probably a non-trivial amount of programming experience. And then we took 3 non-programmers. These are essentially administrative assistants that typically are familiar with Excel and Word, but really haven't had any experience doing programming. Okay, and so in terms of the claims themselves, the general set of users are used to support the second 2 claims here, that it takes less time for the subtasks, and overall we could do it faster. And the non-programmers here were used for this claim here, which is that that someone with no programming experience could actually build the 4 mashup types. Okay, so the setup was the following, which is that for the people that were programmers, since they took this class, we actually had them do assignments in Dapper and Yahoo Pipes in the class. So they already were familiar with these tools. They actually had to do a couple of different assignments for this, and many of them actually used them for projects in the class. But in addition, we gave them a review package prior to the experiment, so that we sent them somebody say, okay, do the following tasks so you remember how to use these tools, since it was early in the semester. And then right before the experiment, we gave them a 30-minute tutorial going through the different systems and exactly how they work, so that everyone was familiar. It wasn't like a new tool to them. And the tutorial was about 15 minutes on Dapper and Pipes, and then 15 minutes basically teaching them how to actually use Karma. Then, since they hadn't previously used Karma, we let them practice on 2 to 3 tasks using Karma, just simple tasks that were different than the experiment one, so they had some familiarity with Karma as well. And then the test, we gave them 3 tasks. And for the programmers, they basically alternated between Karma and Dapper Pipes for each of the tasks. For the non-programmers, they only had them use Karma, simply because we just didn't really think that it was practical for them to use Dapper and Pipes. And then everything was basically recorded using a video capture software. And that was just allowed us to go back and measure the amount of time after the fact, so we could see how much time they spent on the different subtasks. So here's an example of the results. So this is one task here, the different subject numbers, And then we broke out the time based on extraction, modeling, cleaning, and integration, and then the total time. And notice here we have these fives. We basically had a 5-minute cutoff time for the users. And that's simply because many of these users eventually fail on some of the tasks, and we didn't want them to spend all day on this. And then we measured these things for both Dapper and Pipes and for Karma, and then totaled them up. Okay, then the evaluation tasks. We have 3 tasks. They sort of correspond to the original tasks I talked about. So the type 1, which is the simple extraction task, extraction, then put the information on a map. And here we have the different things, the data extraction, source modeling, cleaning, and integration. And we rated, this is our sort of subjective analysis about how hard these different tasks were. And you can see the second task really combined both dealing with the form kind of interface and then doing some union over the data. And again, in this one they had to do the union, a simple cleaning task, a simple source modeling task. And then on the third task, it was a little more complicated where they had to join 2 sources together. The data extraction modeling were pretty simple, but doing this part's a little more complicated. And there was no cleaning for that particular task. And these were real world tasks, real sources that we used. Okay, so let's take a look at the claims one by one. So the users with no programming experience can build all 4 mashup types. And claim 2 was, the Karma takes less time to complete the subtests and scales better as the tests get harder. And you can see here that, we have, different difficulties on some of these tasks that we could compare. And then claim 3, which was, overall the user takes less time to build the same mashup of Karma as compared to Dapper and Pipes. And so we look at, the overall time to do the end-to-end tasks. Okay, so let's look at the first claim here. So here were the results for the non-programmers. And there are only three users here, which is somewhat limited. But really, we were just trying to show a proof of concept, right? That we could take these people, they weren't trained as programmers, and in fact, they could actually complete these tasks. And you can see that, these are the 3 subjects that are color-coded here. We have the time on the axis here, and then the tasks 1, 2, and 3. For the non-programmer subjects, we used a time limit of 10 minutes. So you can see that they're all completed within the time, and they did pretty well. They did pretty well in these tasks overall. Clearly, the red subject took more time than the other 2, but overall they completed the tasks pretty quickly. The second claim, which was Karma takes less time to complete each of the subtasks. So I'm going to just go through quickly each of the subtasks here. So we have the extraction work, and you see again same setup here, which is that these are organized by they're ordered by simple to hard. So this is simple, moderate, and difficult tasks. They're in different orders. This is task 3, task 1, task 2. We order them from easy to hard. And then on the x-axis we have we group the time into different intervals. And on the y-axis we have the number of subjects. And so you can see the Karma is shown in green and Dapper and Pipes is shown in blue. So you can see on the simple task, Karma did better. Then as we get to the moderate and hard task, it continues the same pattern, which is in general, Karma is outperforming Dapper and Pipes across these on the extraction stuff. Which I don't have one with me, unfortunately. I should have brought one with me. But part of it's that we're in the midst of a complete re-engineering of the system, and so with a new version we're supposed to have out on Monday, so it's kind of in flux at the moment. Okay, so here we have sorry.
Try it out for ourselves, or?
No, we haven't made it available. It really has very much been a research project. But we have a movie of it, and I'll put the movie up on the website. You guys can take a look and watch the movie and stuff. It's very much of an active research project where we're looking at improving each of the different components. Now that we have sort of the end-to-end system working, we're working on the different components, and I'll talk a little bit more about that in terms of where we're going next with this. But it's very much work now where we're doing some additional work on sort of expanding the generality, so it'll work on more websites, it'll do more stuff. But eventually we'd like to make it available. Okay, so we see here, not only, one of the things I want to point out here is that, so not only is Dapper performing better in terms of the time, Karma's performing better in terms of the time, but on Dapper and Pipes, you can see that there's a certain number of people that are failing on these tasks. For the simplest one, everyone completes it, but for the moderate and hard tasks, you can see that these are the programmer users. You can see that some of them are actually failing to even complete the task, which is somewhat surprising given that they've all been trained to use those systems. Source modeling is a little different. So what happens in source modeling here is that we have Rattapoom pipes, and you can see now it's actually outperforming Karma, at least on these first two tasks, and that's simply because there isn't so much of a need to do the modeling. I mean, so since they're not really supporting the integration at the same level, it's actually any modeling that has to get done in Rattapoom pipes is actually simpler to do. In this case here, Karma was able to do the modeling automatically because it actually recognized the particular thing that had to get modeled and generated the right type. So it didn't require any time on the user at all. But you see, this time is quite small. So even though Karma performs worse in task 1 and 2, there's a relatively small difference, like on the order of 30 seconds. And you'll see that this savings gets realized in the integration step. So when we actually do the integration, it actually makes life easier for the user. Then we get to the data cleaning step here, and again we see that there are only 2 tasks we had data cleaning, and you can see Karma is doing better than Rattapoom pipes here. And in particular, as the task gets harder, more subjects are failing in the Rattapoom pipes, right? So in this task we're getting about 35% are failing, and here we're getting 83% that are actually failing on the cleaning task. Yes?
So did the students that fail get extra credit?
Oh, absolutely. Otherwise, they'd never forgive you. They were all motivated, though. I mean, I think everyone really wanted to complete the task. So they didn't know how it was going to get scored in the end. Then here we have the data integration step, and there were only 2 tasks where we had to do this. So you can see here that the union task, well, there's almost no work for the user here, so that happens almost immediately, whereas it's quite a bit more work to do this in Yahoo Pipes. And then for this task, you can see most of the users failed here. And this really had to do with the model that happens for doing the joins across in pipes. And it's quite sort of tedious in that the user has to go to this menu and kind of select, which thing you want to join with and stuff. And it's quite time-consuming to do it. So either they ran out of time or they just gave up because it was quite painful to do it. There was 1 or 2 users that were able to complete that. So here we have, again, about 30% fail on the union task and about 95% failed on the join task. Okay, and then overall, so these are really just all the numbers aggregated together, and you can see here for task 1, the green is Karma, which is performing much better. Task 2, again, is performing much better. You can see these times are quite large, and then task 3, overall, again, overall Karma is actually doing much better on all these tasks. Okay, so if we look at the relationship, these are just the speed up or slow down. So on extraction, it was about 2.2 times faster. Source modeling was a little slower. Cleaning was about 4 times faster. Integration was about 6 times faster. And then overall, we get something about 3 times faster, 3.32. Okay, we did the statistically significant test, and so Karma is faster, when we do the averages across these things, except for on the source modeling task, where Rattapoom pipes is faster. Yes.
Did the programmers do the tasks in the same order like they always did, Karma first, or they always did?
No, we switched up the orders. So they would do, some of the students would do, no, there's not. And in fact, we switched them, so there were 3 tasks, and so which task they started first was also very, okay, so now there's been a fair amount of related work. I don't really have time to talk about all the works in general, but let me just sort of describe it in general. There are a number of tools out there. So there are systems like, MIT had a system called Simile, and there's Rattapoom pipes that I've talked about. Microsoft has a system called PopFly, Marmite, Intel MashMaker. So there's a bunch of interesting systems out there that have all tried to do, some piece of this kind of mashup work. If you look at sort of the types they supported, so we're really classifying it from our view of the world in terms of the kinds of things we were doing here, you can see very few of them really tried to do all the different sort of pieces of the integration, right? They do different pieces of this, either the unions or the joins or both. The Intel MashMaker is the only one that really covered all of the same classes of tasks that we did here. And if you look at how the system works, it really requires an expert. Once you get into those kinds of tasks and you read their papers and stuff, you really, to get to the integration tasks where you're doing joins and stuff, basically there's an expert who's basically writing the integration task for you there. So in some sense, yeah, they support it, and I suppose you can become an expert, but I think they have different levels of users, and that's the basic level of user really just sort of invokes a page and it applies the mashup that's been constructed. Similarly, this is sort of fairly early work using the document object model. It was focused on sort of extraction to get data in the semantic web. It was an interesting system, but it supported very limited kinds of work. Their sort of follow-on system here was Potluck, and also creates sort of RDF for semantic web types of stuff, where the user manually specifies the data integration task. Dapper mainly focuses on extraction and really could do some kind of linear type integration, right? And can take information from this source and put it into this other source. Then all these systems are kind of grouped together. These are all doing this sort of widget-based approach. Microsoft Popfly has a much fancier UI and more widgets that you can use. Marmite really uses this kind of workflow-based approach, and in their user studies they found that the users really got confused by the sort of the whole workflow kind of approach. Google My Map would really just take points from some source and stick it on a map. This is some work we did at USC. This is sort of our system that predated this, what we call the agent wizard. And this was more of a question answering type approach, where the idea was that you essentially go through and you ask the user a series of questions to create the mashup. And the problem with this is it didn't scale well in the sense that the questions get quite tedious, and as the tasks get more complicated, there's more and more questions, and you never know when you're going to actually get to the end of the questions. But it's sort of modeled on the the tax program question answering paradigm. You get to the end, you have your mashup, but it wasn't quite what users wanted. This is Cards is another system that's done here at Microsoft, sort of more of a tuple-based approach where everything is sort of mapped into tuples and things are linked between them. And then finally, Karma here on the bottom. So a lot of these systems, they address some piece of the problem and in some sense require, I'd say most of them require sort of more expertise to get to the same level of kind of functionality. Then there's a whole set of work on each of these subproblems, and I'm not going to go through it. There's quite a bit of interesting work on, for example, information extraction. We've done some of this work. We sort of fit into this category here of, on sort of exploiting the document object model. But in fact, we're actually moving to this model here. So in fact, we have a new version of the system where we've actually integrated in some of the work that we've done previously on sort of machine learning type approaches to do the extraction. And this is really just to get more generality for the type of pages we can apply this to. Lots of work on source modeling. Phil here has done a fair amount of work himself on this. And really what we're doing here is just leveraging very simple kinds of techniques in the current system, and we want to integrate in more sophisticated kinds of mapping stuff. Data cleaning, there's been a lot of interesting work on data cleaning, and we're really just providing a generic model where many of these techniques, in fact, could actually be integrated in. And then the integration piece, I think the most close related work here is other work on programming by demonstration. Tessa Lau, for example, has done some work at the University of Washington on this. She did her PhD on that. And, there we're, applying similar kinds of techniques, but doing it in sort of a new framework and in sort of a novel way. Okay, so let me just wrap up. Clearly, mashups are here to stay. There's a lot of interest in, this whole idea of being able to take existing sources and put them together in novel ways. And the need here is, to find some nice way that really allows end users, the web users out there that use browsers today, to do the same kind of thing where they can build their own mashups. So our contributions here is this, programming by demonstration approach, where we use this single table as the unifying sort of paradigm to pull the information together. We solve really these four pieces that we view as sort of central to sort of the mashup construction: the extraction, modeling, cleaning, and integration. And then this sort of query formulation technique that really allows the user to sort of specify more complicated kinds of integration and stuff, where they can say, okay, I want to integrate this source or this other source in this way, which I think is fairly natural for the user, but maps to fairly complicated queries under the hood. And then finally we evaluated sort of demonstrated the validity of this approach by showing that real users could actually complete these tasks and get some significant improvement over existing approaches. we're very interested in sort of future work. We're already working on some of these. One area we've done almost no work is just customizing displays by example. I think this is a really interesting topic, which is that one of the things you see if you look at all the different Mashups tools out there is that there's a huge number of different kinds of clever interfaces and displays that people use for Mashups. We've really ignored all that and just sort of say, well, we'll just allow people to put it on maps. But there's, I think, a really interesting opportunity there for allowing the end user to customize the display. Another area that we're interested in pushing on is learning and generalizing over the tasks. We really want to be able to store the integration plans and then re-execute them on new data as the information is changing on the web and stuff. And this is really sort of a natural extension of what we have here, but it's not in the current implementation. The next one I mentioned is work on machine learning for extraction of tasks. And in fact, we're doing this work in collaboration with Fetch Technologies because they've been building new tools for automatically wrapping form data and then automatically extracting the data that on the result page from the forms. And so we're looking now at sort of integrating some of that new technology into this so that we can get sort of more coverage, things that aren't handled well by sort of the document object model approach. And then we have some other work that we've been doing in the past on integrating, work on automatic source modeling. And right now we're using something fairly simple in Karma. We want to integrate that piece in where we actually do sort of more sophisticated kinds of models where you actually learn from the data you've seen in the past and you say, okay, I recognize this particular date format. And once you know what the date format is, then you can normalize it and put it in a standard format, that kind of stuff. And I think, I just mentioned there's a couple of papers. These are available on my webpage. One appeared in the 2008 IUI conference. The other one was in the 2007 IUI conference. So if you're interested in reading more, those are the papers. So that's it. Thank you. Questions? Did you guys exhaust all your questions?
When you have a demo, or say like a user interactive demo available.
A user interactive demo? I know that's a longer process because to get to the point where you can actually put up a tool for people to use requires you get to a particular level of the software, and it's not. We're Yeah. Oh, we do. We do. But then, putting it up on the web is sort of more complicated, right? So either you have a piece of software that you have to allow people to download and install, or you have to have some kind of web-based interface that allows them to use it and stuff. So, when we had users test it, we said, here's the computer. We put the computer in front of them and they let them run the software. So it's just a matter of sort of resources and cycles to sort of support that kind of thing. But I will put up the video because, I really should have brought the video with me so I could show it now because it's nice to see what the system actually looks like. Yes.
So for the machine learning information extraction part, so I guess I'm kind of curious how you plan on doing that with like the user, because the user would sort of have to interact to set the boundaries of the extraction rate, or?
Yeah, so the way that works is we have the interaction now. So we have an initial version where right now you copy and paste the data from the web page into the form, and now we're just using that data as the labeled training data to do the extraction. So in some sense, and what's happening in the system under the hood is every time the user copies and pastes any piece of information to the table, it basically treats that as a learning task, goes off, tries to learn the extraction, generates the data it would produce, and maybe it's what the user wants, maybe it's not. The user can refine it by bringing more examples. So it takes a stab based on the first example, and then if the system doesn't get it right, the user copies more examples and brings it in. But it's not as closely tied to the document object model. That's the real advantage. The disadvantage is it may require more interaction. And we're talking about maybe some hybrid approach where when you can get it using the document object model, you can do that, and then when you can't, then you can use this more sophisticated approach.
Already extracted is like if you're integrating with restaurant names, maybe you can find all the matching names on the page, or
no, potentially it's a good idea. But there's another path to go, which is that people have been doing more work on sort of just automatic extraction from pages themselves. Where so another model we're exploring is you basically automatically extract the data off a page. And you're essentially trying to segment the data into different pieces of information. And then given an example from the user, what that example tells you is, well, what information the user's looking for on that page. And then you can actually pull that information out. Which I think is probably the most promising approach because that really is going to minimize the amount of training data. The issue with previous work on sort of machine learning for building wrappers and doing the extraction is simply the amount of training data that it takes to really get it right. And users have limited patience for providing training data in the real world, right? Ideally, they want to get it in the first example. And maybe they'll be willing to give you a second example. And after that, they throw up their hands and say, it's a stupid system. Other questions? Yeah.
Are you doing anything with web services at all, or is it all just rendered web? Basically, what you just scraping it on?
Actually, we've more recently looked at, we have a version of the system now where we do the extraction. We can do the extraction from Excel. We haven't done web services, but there was one other sort of, and just plain text files. But there's no reason we couldn't add web services to that as well. That would be quite natural. So yeah, but we have been trying to generalize the set of sources because not everything is in a web page. Yes?
We launched a project called Calstream for watershed organization in Southern California, very similar to this project, but organizations can link their databases to the wiki pages, and users can query to the databases and extract information and do some kind of data analysis and integration. And the problem that we are facing these days is that experts are somehow reluctant to contribute in the wiki because, for example, they're not sure if another user come to their pages and manipulate the data, and they like to lock their pages.
Right.
So, and they are very concerned about the credibility of the source of information that other users actually link to the wiki,
right.
And they are looking for some ways to filter the reliable data out from the unreliable data in order to save them in their own databases.
Right.
So now my question is, do you have a policy for defining access rights for different types of your users? Because I'm sure you will have some experts in your system, some users from public.
Well, our model for the system is that this is a tool that a user would download and use or use on the web, and so we don't really have any need for access rights. They're really just going out to public sources or publicly available sources and pulling them together and building their integrated tools. We're not really we're not making any data available ourselves, and so we don't really have to provide any kind of access information. It's a slightly different problem, right? Because you're in the position where you're trying to sort of manage your own users' data and who's going to have access to it and what they're going to do with it.
No, actually, there are some people in public that they go to California beaches, they do sampling from the water, so there's that voluntarily they like to share their information through the wiki with other people.
Right.
So it's not just necessarily just. I mean that we cannot assume that the data is just from the databases, so people can go and gather some information themselves and add to the wiki.
Right. There's a larger issue here in general, which is, what's the overall business model here for the people providing the data, right? If I'm a data provider, maybe it's a publicly available data source like the LA County Department of Health. That's just a public service. Your tax dollars pay to have that data available. But you could imagine that, well, with health ratings and those kinds of things, then there's the issue of, well, how are those organizations making money, and are you circumventing their business model by extracting and integrating the data and stuff? So those issues, I haven't taken any position on here. We're looking at the technology to be able to put stuff together, but those kinds of things still are open issues. Any more questions? Okay. Thank you.